Tambac, and this is my final report number 1, Chapter 10, Vectors and Planes, Lines, and Surfaces in Space, Section 3.1. 3.3. Dot product. So far, we have defined the following operations with vectors, additions, and subtractions, and multiplication of a vector by a scalar. Each of these operations results in a vector. We now define a multiplication operation on two sectors, called the dot product, which yields a scalar and not a vector. In definition 10.3.1 of dot product, the dot product of two vectors A and B denoted by A times B is defined as follows. If A is equal to A sub 1 times A sub 2 and B is equal to B sub 1, B sub 2 are two vectors in V sub 2, A times B is equal to A sub 1, B sub 1 plus A sub 2, B sub 2. If A is equal to A sub 1, A sub 2, A sub 2, and B is equal to B sub 1, B sub 2, B sub 3 are two vectors in V sub 3. A times B is equal to A sub 1, B sub 1 plus A sub 2, B sub 2 plus A sub 3, B sub 3. The dot product is sometimes called the inner product of scalar product, not to be confused with scalar multiplication, which gives the product of a scalar and a vector. In illustration 1, if A is equal to 2 and negative 3 and B is equal to negative 1/2 and 4, then A times B is equal to 2 and negative 3 times negative 1/2 and 4 is equal to 2 times negative 1/2 plus negative 3 times 4 is equal to negative 13. In illustration 2, if A is equal to 4, 2 and negative 6 and B is equal to negative 5, 3 and negative 2, then A times B is equal to 4, 2, negative 6 times negative 5, 3 and negative 2 is equal to 4 times negative 5 plus 2 times 3 plus negative 6 times negative 2 is equal to negative 2. Dot product involving the unit vectors ij and k are useful and easily verified, as we see in exercise 5 and 6. I times j is equal to 1, I times j is equal to 0, j times j is equal to 1, I times k is equal to 0, k times k is equal to 1, and j times k is equal to 0. The following theorem states that dot multiplication is commutative and distributive with respect to vector addition. In theorem 10.3.2, if A, B, and C are any vectors in V sub 2 or V sub 3, then A times B is equal to B times A, or commutative law. A times B plus C is equal to A times B plus A times C, or what we call distributive law. Because A times B is a scalar, the expression A times B times C is meaningless. Hence, we do not consider associatively of dot multiplication. Other laws of dot multiplication are given in the following theorem. In theorem 10.3.3, if A and B are any vectors in V sub 2 or V sub 3 and C is any scalar, then C times A times B is equal to CA times B. 0 times A is equal to 0. A times A is equal to cardinality of A raised to the power of 2. The proofs are left as exercises C, exercises 9, and 10. We now consider that is meant to be the angle between two vectors, and this leads to another expressions for the dot product of two vectors. In definition 3.3, 10.3.4, definition of the angle between two vectors. Let A and B be two non-zero vectors. If A is not a scalar multiple of B, and if OP is the position representative of A and OQ is a position representative of B, then the angle between the vectors A and B is the angle of positive measure between angle OP and angle OQ, anterior to the triangle determined by the points OP and Q. If A is equal to CB, where C is a scalar, then C is greater than 0, the angle between the vectors has radius measure 0. If C is less than 0 and the angle between the vectors has radius measure pi. The symbol used to denote the angle between two vectors is also used to denote the measure of that angle. From the definition, if theta is the radian measure of the angle between two vectors, then 0 is less than or equal theta is less than or equal to pi. Figure 1 shows the angle theta between the vectors A and B, where A is not a scalar multiple of B. In V sub 2 and figure 2 shows the angle when the vectors are in V sub 3. 10.3.5 theorem. If theta is the angle between the two non-zero vectors A and B, then A times B is equal to cardinality of A and B cosine theta. Proof. Figure 3 shows the position representation of an angle OP of A, the position representation of an angle OQ of B, the representation of an angle PQ of B minus A, and the angle theta at the region in triangle POQ from the law of cosines. Cosine theta is equal to cardinality of A squared plus B raised to the power of 2 minus B minus A squared all over 2 cardinality of A and B. From the properties of the dot product in theorems 10.3.2 and 10.3.3, B minus A squared is equal to B minus A times B minus A is equal to B minus A times B minus A times A is equal to B times B minus A times B minus B times A plus A times A is equal to cardinality of B squared minus 2A times B plus A squared. Substituting from 2 and 2 to 1, we get cosine theta is equal to A squared plus B squared minus B squared minus 2A times B plus A all over 2A and B. Cosine theta is equal to 2A times B all over 2 cardinality of A and B. A times B is equal to absolute value of A, B cosine theta. Theorem 10.3.5 states that the dot product of two vectors is the product of the magnitudes of the vectors and the cosine of the angle between them. Example 1. Given the vectors A is equal to 6i minus 3j plus 2k and B is equal to 2i plus j minus 3k. Find cosine theta if theta is the angle between A and B. Solution. We first compute A times B, cardinality of A and cardinality of B. A times B is equal to 6, negative 3, and 2 times 2, 1, and negative 3 is equal to 12 minus 3 minus 6 is equal to 3. Cardinality of A is equal to square root of 36 plus 9 plus 4 is equal to square root of 49 is equal to 7. And cardinality of B is equal to square root of 4 plus 1 plus 9 is equal to square root of 14. From theorem 10.3.5, cosine theta is equal to A times B all over cardinality of AB is equal to 3 all over 7 square root of 14. You learn on section 10.1 that if two non-zero vectors are scalar multiple of each other, they have either the same or opposite directions. This fact gives us the following definition. 10.3.6 Definition of parallel vectors. Two vectors are said to be parallel if and only if one of the vectors is a scalar multiple of the other. Illustration 3. The vectors 3, negative 4 and 8 and 3, 4, negative 1 and 2 are parallel because 3 and negative 4 and 8 and is equal to 4, 3 over 4, negative 1 and 2. If A is any vector, 0 is equal to 0A. Thus, from definition 10.3.6, the 0 vector is parallel to any vector. As an exercise, you are to show that two non-zero vectors are parallel if and only if the radian measure of the angle between them is 0 and pi. If A and B are non-zero vectors, then from theorem 10.3.5, cosine theta is equal to 0 if and only if A times B is equal to 0. Because 0 is less than or equal to theta less than or equal pi. It follows from this statement that theta is equal to 1/2 pi if and only if A times B is equal to 0. We have then the following definition. 10.3.7 Definition of orthogonal vectors. Two vectors A and B are said to be orthogonal perpendicular if and only if A times B is equal to 0. And now we have illustration 4. The vectors negative 4, 5, 0, and 10, 8, and 3 are orthogonal because negative 4, 5, and 0 times 10, 8, and 3 is equal to negative 4 times 10 plus 5 times 8 plus 0 times 3 is equal to 0. Therefore, it is orthogonal. If A is any vector, 0 times A is equal to 0, and therefore the 0 vector is orthogonal to any vector. Example 2. Given A is equal to 3i plus 2j and B is equal to 2i plus kj, where k is a scalar. Find A, k such that A and B are orthogonal. B, k such that A and B are parallel. Solution. A. By definition 10.3.7, A and B are orthogonal if and only if A times B is equal to 0. That is, 3 times 2 plus 2 times k is equal to 0. K is equal to negative 3. B. From definition 10.3.6, A and B are parallel if and only if there is some scalar C such that 3 and 2 is equal to C, 2k, that is 3 times 2C and 2 is equal to ck. Solving these two equations simultaneously, we obtain k is equal to 4/3. Example 3. Prove by using vectors that the points A of 4, 9, and -1, B, -2, 6, +3, and C, 6, 3, and -2 are the vertices of the right triangle. Solution. Triangle CAB appears in Figure 4. From the figure, it looks as if the angle at A is the one that may be a right angle. We shall find VAB and VAC, and if the dot product of these two vectors is 0, the angle is a right angle. V angle AB is equal to -2, -4, 6 minus 9, 3 minus 1 is equal to -6, -3, and +2. V angle AB times V angle AC is equal to -6, -3, -2 times 2, -6, -3 is equal to -12 plus 18 minus 6 is equal to 0. V angle AC is equal to 6 minus 4, 3 minus 9, -1 minus 1 is equal to 2, -6, -3. Conclusion. V of angle AB and V of angle AC are orthogonal, thus the angle at A in triangle CAB is a right angle and CAB is a right triangle. A geometric interpretation of the dot product is obtained from the scalar projection of one vector onto another. See Figure 5 where OP such that OQ are the position representation of vectors A and B respectively. Prove R is the foot of the perpendicular from Q to the line containing OP. The scalar projection of B onto A is the magnitude of vector having OR as its position representation. And that would be all. Thank you and God bless us all.